Welcome back to Discrete Mathematics. Today we're going to take a look at Euler circuits and Euler trails. So let's get into it. We're going to let G be an undirected graph with no isolated vertices, and we say that G has an Euler circuit or trail if there's a circuit or trail in G that traverses every edge in G exactly once. So here's an example. We want to make an Euler circuit from A to A. So it's a circuit, so clearly it goes from A to A, but we need to use every edge exactly once, which means we can't backtrack, but we have to hit every edge. So let's go here. Let's start at A. We're at A, and let's take this edge to the right here. Okay, that's good. And let's go past, take this edge down here, move all the way down, and, well, we probably want to go back to the vertex we were just at to finish up all of its edges. So we'll go up here. We'll take this path down to the left. We have a nice triangle here, so let's just wrap around that. We can't return to A yet because we haven't used all the edges. So we'll go around here, and then we'll finish it up and move back up to A. You can see that we traversed every edge exactly once, so this graph has an Euler circuit. In fact, you can kind of see it's symmetrical, so if you can do it one way, there's a good chance you can just do it in reverse on the opposite side. So it's not always a guarantee, but it's an interesting thing to think about. In fact, if you saw here, really what we had was 3 triangles. So when you have these 3 triangles, you can kind of just break it into separate triangles and then just loop around, go to the next one, loop around, go to the next one, so on and so forth. So that is an Euler circuit. So we can prove things about certain graphs, and we know that. So we're going to prove that a graph has an Euler circuit if 2 conditions. G is connected. And the second condition, every vertex has an even degree. So let's say if Euler circuit, then connected and even degree. So let's say here, okay, so there's an Euler circuit, the graph definitely has one. So clearly, the graph has to be connected. And I'm going to show you an example. And you can do this in words in your proof. I'm not going to write out word for word, I'm just going to kind of show you with pictures what's going on here. So suppose, let's take a very simple Euler circuit. So we see here that we can go from A to A and use every edge exactly once. That's pretty straightforward. We just go down, up, and back up. But if we have a disconnected graph, so let's say we have a portion over here with this edge, well, it's impossible to get over to that edge to use it. So clearly, it can't have an Euler circuit if it's disconnected. So if there is an Euler circuit, we know the graph is going to be connected. And every vertex has even degree. So what does that mean? Well, let's take a look. Let's call this part 1 over here. And part 2 here, let's take a look at a graph with odd degree, where one vertex has, or sorry, 2 vertices have odd degree. So let's do, actually, I know what we'll do. We're going to give this one 2 edges. We're going to give this one 1 edge. So we want to go from A back to A. So here's what happens if we have a vertex of odd degree. We leave. Okay, we leave A. And now we can't ever return. Ever. So we can't have an Euler circuit. So if the graph has an Euler circuit, then clearly G has to be connected. And every vertex must have even degree because we have to leave and return. So if there is an Euler circuit, we know for sure that it's connected and it has even degree. So let's prove the other way, which is a lot harder. I'm going to outline the proof in words and then we'll go through it. So we're going to do an inductive proof on edges. So we're going to show that if there's 1 edge and 2 edges where the graph is connected and has even degree, then we can construct an Euler circuit. Then what we're going to do is just assume that some graph has k edges, and then we're going to add an edge, and we're going to see if we can reconstruct an Euler circuit from it. So we're going to build a circuit, we're going to decompose into some smaller circuits, and then we're going to rebuild it and show that we have an Euler circuit. So let's do the base case. We have to show that when the edges are equal to one edge or two edges, it's true. So let's let e equal 1. So if there's one edge, then, well, we're going to have a loop. So there's a loop. So we can go all the way around, and that's an Euler circuit. Okay. And if we have two edges, so remember here, edges has to be 1 because, or sorry, the number of vertices has to be 1 because it's connected and every vertex has even degree. So those are the conditions that we're saying, okay, it is connected, it does have even degree, so this is the only way we can make it connected and even with one edge. Okay, so here's edges equal 2. So we want e equal to 2. Well, there's actually two cases here. One case is we have two loops. So I'm going to actually do this like this. Well, clearly there's an Euler circuit because we can go on this edge, then on this edge in any order. But another case is when we have, actually, can we do this here? Yeah, I think we can. So we can do this sort of graph. So we can go from A to B, and then we can go from B back to A. So those are the only two graphs we can do where the edges are 2, where again the graphs have to be connected and each vertex has to have even degree. So that's the base case. Now for the induction hypothesis, we're going to assume that n less than k edges are true. So this is a strong induction. So we're not just saying that when it has k edges it's true. We're saying that if it has any number less than or equal to k, it's true. So this is strong. And we want to show that the edges equal to k plus 1 has a circuit. So here's what we're going to do. We're going to take a graph. We're just going to call it graph G. And we're going to say it has k edges. So we don't know what it looks like. But we're going to start looking at the edges here. So it's some graph. Let's take this graph, for instance. Okay, this has 1, 2, 3. I'm going to use a nice small graph just to show you that it works. So let's do this. I just need to make sure each edge has even degree, which it doesn't. Okay, does that have even degree? We have one problem here, so we're going to do that. Now, it looks like this graph obeys everything I want it to. Okay, so it's connected, and each vertex degree is even. Okay, so what we're going to do is we're going to construct an Euler circuit. Well, we're not going to construct an Euler circuit, we're just going to construct a circuit. So we're going to start here, and we're just going to construct a circuit. So let's do that. Let's say, okay, we go here, and we're just going to go around. So there we go. That's a circuit. We're going to call that circuit C. And what we're going to say is that, well, it's connected and each vertex degree is even, so we know there is some circuit in there. Doesn't matter where the circuit is, doesn't matter how long it is, we're just going to have a circuit. So there's two cases here. Case 1 is that we pick a circuit that is an Euler circuit. And if that's the case, then we're done, because we've proven that the graph has an Euler circuit. But the case that we're actually interested in is the case where you pick a circuit and it's not an Euler circuit. So what do we do then? Well, we're going to copy and paste our little graph here, and we're going to deal with this. Okay, so what happens if we pick not an Euler circuit? Here's where the fun part comes. We're going to decompose it, which means everything on our original circuit we are just going to delete. Okay, so get rid of the pink there. So this is what we're left with. We deleted our original circuit. So here's the thing. When we do that, what do we notice about the leftover components? Well, the leftover components are all Euler circuits. So there's an Euler circuit here and an Euler circuit here. And what do we know? Well, it's going to be a connected graph still. It's going to be a graph with even degree vertices still. And what do we know? Well, we assume that if it had less than or equal to k edges, then it was true that it had an Euler circuit. So we know that whatever components remain have an Euler circuit based on our induction hypothesis. So because of our strong induction, if we make this any graph we want, the graph we're working with, it can be any different graph, we know for sure that all the remaining components have Euler circuits. So we've decomposed it. Now what do we do? Well, what we're going to do is we're going to start back at our original position. And you remember we had our original circuit. So what we're going to do is we're going to move along that circuit. So we get here, we get to the next spot. And then whenever you touch a vertex that has an Euler circuit, we're going to take that Euler circuit. So we're going to go all the way around. So we now covered this Euler circuit. And then, because this had a mini Euler circuit, we're going to start and end at the same spot. So we're going to continue along the original path. And then, what do we got here? Well, we hit another Euler circuit. So let's take that. Okay, we're going to go through here, take it back. And now we're going to continue along the original circuit we chose. And now we have a full Euler circuit. So the proof is complete. I didn't write down too many words because it takes a lot to write a lot of words. Textbooks do it good. This proof is on the internet in text, so hopefully now that you've seen visually what's going on, you can take a look at a textbook and see it in words and understand it. So let's go over this again quick. I'll do a little recap here. So we're going to show that if connected and even, so connected and even degrees, because we want to take these two, and we want to show there's an Euler circuit. So we assume that. So we said, okay, if there's one edge, we can do it. If there's two edges, yes, it's going to have an Euler circuit for sure. So the base case is shown. For the induction, we said, okay, let's say all edges less than or equal to some number k is going to have an Euler circuit. And then we're going to say, let's go one step further and show that that has a circuit. Let's add an edge. So we take any graph we want and we construct a circuit. There's two cases when we do that. And I should say we know there's at least a circuit because connected and even degrees mean that you can leave and enter every single vertex, so there must be some path to get back to the original. Okay, so that's been done. If we pick a circuit nicely, it could be an Euler circuit right away. If not, then what we do is we delete the original circuit. So we delete all those edges, and we delete our little pink circles, and then what we do is we take a look at the remaining parts, and because our induction hypothesis said for n less than or equal to k, it has an Euler circuit, we know that the number of edges in our components are going to be less than k. So that means that when we reconstruct our circuit, we can just take the Euler circuits as we hit the vertex that contains them. and then we construct a full Euler circuit in the graph. So that's the proof. A little complicated, definitely the first complicated graph theory proof you've probably seen, and it's going to get probably about the same difficulty for the rest. So conceptually, visually, if you can do this visually, you can figure out the words to make it work verbally or written. So hopefully you understand the main concepts behind that. So let's take a look at directed graphs. So directed graphs have a different degree structure. The total degrees in a directed graph is still 2 times the amount of edges, but because directed graphs have directions, which means there's heads and tails, we talk about in degree and we talk about out degree. So this is in, this is out. So an in degree is when the head points to it, and an out degree is when the tail comes out of the node. So let's take a look at the in degree of A. So we take a look at A here, and we say, okay, nothing's coming into it. So the in degree is 0. But what is the out degree? Well, we have one edge going to C and one edge going to B. So the out degree is 2. Okay, let's do B. The in degree, well, it has nothing going out. So it has an in coming from A and an in coming from C. So the in degree of B is 2. And B doesn't go out to anything, so the out degree is 0. Okay, what about C? The in degree has 1 coming from A, but it also has 1 coming from itself. So that's 2, because 1 comes from A and 1 comes from itself. Now the out degree has 1 going to B, but it also has 1 going from itself to itself. So this is plus 1 going to B and plus 1 going to itself. So that's 2. So when you have a loop, you have in degree plus 1 and you have out degree plus 1. So again, just like when you have a CC here, let's take a look at how we write edges. So remember, in directed graphs, when we have an edge, it's ordered. So we have CC. The first position is always going to be the out degree, and the second position is always going to add to the in degree. So when we have CC, it adds 1 to the out degree for C and 1 to the in degree for C. So that is how we do directed graphs. So why do we need directed graphs, and why do we need Euler circuits and trails? This is really complicated and I don't really see an application. Well, lucky for you, there's a nice application that takes in directed graphs and Euler circuits. So, rotating drum. Here's what a rotating drum does. It connects to 3 different nodes here. So what we have on the right is some display. So this might say 101, and this corresponds to the numbers on a drum. So this drum right here, it's going to rotate in water or in some electrical plant. Who knows what it's for, but it's going to rotate. And based on the 3 inputs here, we are going to know what position the drum is at. So let's say we're measuring strength, and it has some resistance meter, and when it's at 0, 0, 0, it's not moving at all, but when it's at 1, 1, 1, it's moving really, really hard. And it turns based on how much flow we have going through. So it's a little bit hard to imagine and probably doesn't obey the laws of physics, but it could measure strength. So what we want is we want to put down a binary sequence of digits so that no reading is exactly the same. Because let's say we have 1, 0, 1, 1 here. If this all moves over 1 position, then the new reading is going to be 0, 1, 1. So this will get replaced with 0, 1, 1. So we want all of these different readings to be different when we rotate it. So how can we figure out a nice sequence to put on this drum? Well, we're going to use an Euler circuit. So an 8-bit string is we're going to require that we have 4 vertices. A 16-bit string would require 8 vertices. So when you double the string, you double the vertices. So let's take a look at how we construct this. So we're going to do this with a graph. And how do we construct the graph? Well, what we do is we take this 1, 0 here. We're going to start with 1, 0. And let's say we have a node 1, 0. When we connect it to something, we're going to take 3 digits. The first digit is going to be the 1, the second digit is going to be the 0, and the third digit is going to be the vertex that we point to. But what's going to happen here is when we take a look at, say, another node, let's take a look at 1, 1. Let's say we're going to 1, 1. The first digit's going to be unknown, the second digit's going to be 1, and the third digit's going to be 3. So the node that we come from is going to have the first 2 numbers, and the node that we go to is going to have the last 2 numbers, which means that these 2 positions here have to be the same number. So as an example, this 1, 0 can go to 0, 0. Let's just do this. So 1, 0 can go to 0, 0. So we get a 1, 0. Let's do this on the outside here. We get a 1, 0 from the first node, and then we go to 0, 0, which gives us the second and third numbers. So this edge is going to be 1, 0, 0. So just to show this, we have 3 positions. We come from 1, 0, we go to 0, 0, and this is all going to collapse to give us 1, 0, 0. Let's do another example here. We're going to go from 1, 0 to 0, 1. So we're going to get 1, 0, 1. So let's see how this works. We take the 1, 0 from the first number and the 0, 1 from the second number, or the second vertex, and this collapses down to 1, 0, 1. Okay, so let's just spell out the rest here. We're going to do this for all the possible values. So we can go from 0, 0 to itself and get 0, 0, 0. Go from 1, 1 to itself and get 1, 1, 1. 0, 1 can go back to 1, 0 and we'll get 0, 1, 0. 0, 0 goes to 0, 1 to give us 0, 0, 1. 0, 1 goes to 1, 1 to give us 0, 1, 1. And 1, 1 goes to 1, 0 to give us 1, 1, 0. So you can do that example for all of these. Just mention these have to be the same. So you can test each one individually, collapse it, but this is the resulting graph we get. Now what we'll do is we need to make a sequence somehow. So what we're going to do is we're going to construct an Euler circuit. So we can start wherever. Let's start at 0, 0. Then what we'll do is we're just going to draw as we go. So we're going to go from 0, 0. We're going to take this edge right here and go back to 0, 0. Then we're going to go, well, we can only go to 0, 1 right now. So let's take this edge and go to 0, 1. Okay, now with 0, 1, let's go up to 1, 0. Okay, and then we can go back down to 0, 1. Okay, and then let's go all the way up to 1, 1. Just keep following the edges one by one. Then we'll take 1, 1, we'll loop it back around to 1, 1. Then the only place we can go now is 1, 0. And then we have to loop back to 0, 0. And that ends the circuit. Okay, so we need an 8-bit string. Well, let's take a look at this. We have 1, 2, 3, 4, 5, 6, 7, 8 vertices in our circuit. So what should we do? Well, we take the first number from each of our vertices, and then we just make a list of those numbers, and we follow the Euler trail. So we're going to get 0, 0, 0, 1, 0, 1, 1, 1. And this is going to be our binary sequence that fits into the drum. So 0, 0, 0, 1, 0, 1, 1, 1. So let's put that in here. Okay. We got 0, 0, 0, 1, 0, 1, 1, 1. Let's make sure that there's no repeated sequence here. So we can start at this node and get 0, 0, 0, or we can move it to the left one and we'll get 0, 0, 1, 0, 1, 0. Okay, so now let's start at the 1 here. We're going to get 1, 0, 1, 0, 1, 1. Then we'll start here and get 1, 1, 1, then 1, 1, 0, and 1, 0, 0. I see no repeats here. So that's good. We've covered all 8 possible binary strings. And it was constructed from an Euler circuit. So tell me why you think this works in the comments. And if you have any questions, you can also leave them there. You can check out TrevTutor.com for more materials. And if you have questions, leave them in the comments or at reddit.com/r/TrevTutor. Hopefully this helped, and I hope you guys have a great day.